We'll now discuss the reactions of amines, and we're going to start off with a review of nucleophilic acyl substitution that involves ammonia, primary amines, and secondary amines. An acid chloride, for example, can react with ammonia to produce a primary amide. The ammonia attacks the carbonyl carbon and eliminates the chlorine to give you this amide plus ACl as a byproduct. A primary amine can do the same reaction to give you a secondary amide, and a secondary amine can react with an acid chloride to give you a tertiary amide. Note that tertiary amines are not able to do this reaction since they're not really nucleophilic. Addition of a tertiary amine to an acid chloride would lead to a nitrogen that has 4 bonds on it and a positive charge, which is not a stable intermediate. Ammonia, primary amines, and secondary amines can react with alkyl halides to undergo alkylation reactions. For example, ammonia will react with an alkyl halide in the presence of base to produce a primary amine, at least initially. Primary amines will react with an alkyl halide, again through an SN2 reaction to produce a secondary amine. A secondary amine will react with an alkyl halide to produce a tertiary amine, and finally a tertiary amine can also react with an alkyl halide to produce a quaternary ammonium salt. It is generally very difficult to control these types of alkylations. For the most part, the products would usually be more reactive than the reactant because of the electron donating alkyl groups. And so this reaction is usually not used to do an alkylation reaction. The Gabriel amine synthesis is a method that is used specifically to prepare primary amines from an alkyl halide. In this synthesis, we start off with phthalimide, which is shown here, and we add base, which will remove the hydrogen on the nitrogen. It's a very acidic hydrogen. Think of this very similar to 1,3-dicarbonyls. You might recall that the carbon in the center was very acidic. For the same reasons, the nitrogen here in the center is also very acidic. Adding an alkyl halide to the conjugate base of phthalimide will lead to an SN2 reaction, adding an alkyl group now onto the nitrogen. Hydrolysis of the product that is shown here with base and water, or even acid and water, will hydrolyze the 2 amide bonds that are found around the nitrogen and release the amine as a primary amine. The 2 carbonyls will become carboxylic acids as the hydroxyl or the hydroxide ion attacks one of the carbonyls at a time and eliminates the nitrogen. Another equivalent of the hydroxide ion will do the same with this carbonyl. In this question, we want to use an alkyl halide to prepare the following neurotransmitter, dopamine. Notice dopamine has a nitrogen here that is primary since we have 2 hydrogens attached to it. It's also attached to this carbon, which is attached to another carbon, and then that is attached to a benzene ring with a couple of hydroxyl groups. There's a few reactions we can use in order to make dopamine, specifically the amino group on dopamine. We can, for example, use an alkyl halide and add sodium azide, which will do an SN2 reaction on this carbon by replacing the bromine. That would give us an alkyl azide, which we can reduce with lithium aluminum hydride to produce a primary amine. Another route to dopamine involving an alkyl halide would be to react this alkyl halide with phthalimide after we have added base to it, which would lead to the nitrogen attacking the carbon, eliminating the bromine, and now that alkyl group will be attached to the nitrogen. Hydrolysis of these amide bonds with hydroxide and water would lead to release of the amino group and give us a primary amine as shown here. Another reaction involved in amines is called the Hofmann elimination. This is a reaction that converts amines into alkenes. Amines in general are very poor leaving group, very similar to alcohols. And so if we want to eliminate an amino group, we have to essentially activate the amino group. One of the ways we can do this is by adding an excess of methyl iodide, which will turn the nitrogen into a quaternary salt. Following this up with a base and a mixture of silver oxide and water will make hydroxide ions, which will help eliminate the quaternary salt, which is a much better leaving group than the amino group is. This reaction typically gives you the anti-decisive product. As you can see by this example, the base could remove two hydrogens, either the hydrogens on this CH2, that will lead to the decisive product or forming a double bond this way. Instead, one of the hydrogens on the methyl group is removed, and we end up with a double bond on the least substituted carbon, and giving us, in this example, one hexene. Once the hydrogen is removed, the nitrogen will be eliminated this way to give us trimethylamine. The product from this reaction is sometimes referred to as the anti-decisive or the Hofmann product, and is always the least substituted alkene that is possible from an elimination reaction. Here's another example of the Hofmann elimination, starting with this primary amine. If we add an excess of methyl iodide, we'll have now this quaternary ammonium salt, which when we add silver oxide and water and heat it, we'll get two potential products, either the decisive or the Hofmann alkene. The decisive product will result from the hydroxide ion removing a hydrogen from this carbon and giving us a double bond this way once we eliminate the nitrogen. The Hofmann product, which is the major product from the Hofmann elimination, results from removing a hydrogen from this methyl group, which is more accessible, creating a double bond here after elimination of the nitrogen. Here's a look at the mechanism for this reaction, which is essentially an E2 reaction. The hydroxide ion will remove a hydrogen from a carbon that is adjacent to the carbon that has the quaternary ammonium salt. Removal of that hydrogen will lead to forming a double bond once we eliminate the nitrogen. The reason why the Hofmann elimination gives you the least substituted alkene is because the base will have a hard time getting to the more hindered internal hydrogens like these here compared to the more accessible CH3 hydrogens, which are at the end of the molecule. This is in part due to the very bulky multi-substituted nitrogen or the ammonium salt that we form first before adding the base. The Hofmann elimination appears in the biosynthesis of nucleic acids, specifically adenosine. Adenosine is made in part by a Hofmann elimination of this compound here, which involves removing a hydrogen with base leading to a double bond after elimination of this positively charged nitrogen. That produces fumarate, which has a double bond as shown here. It also releases adenosine monophosphate. In this question, we want to figure out the product that you would expect from the Hofmann elimination of the following amine. Notice this nitrogen is attached to an ethyl group and a cyclohexyl group. When trying to do a Hofmann elimination on an unsymmetrical alkene such as this one, there's two possible outcomes that we can get. The reaction starts by adding excess methyl iodide to the amine that we're starting with. That would lead to adding two methyl groups to the nitrogen and giving us the following intermediate. It will have two methyl groups, an ethyl group that was already on there, and a cyclohexyl group which was already on there. We'll also have a positive charge on the nitrogen. We'll have a counter ion and iodide. Then once we add silver oxide and water, we can do the Hofmann elimination portion of the reaction. The hydroxide ion can remove a hydrogen on this carbon. So let's draw that out. If we have a hydrogen here, we can remove that hydrogen. So base will remove that hydrogen. These electrons will lead to a double bond forming there by elimination of the nitrogen, which notice has two methyl groups as well as a cyclohexyl group. So that would lead to the products that you see on the top, ethylene, as well as this dimethyl cyclohexyl amine. The other possibility is that we remove instead a hydrogen from the cyclohexyl group, so base. We remove this hydrogen, form a double bond here by eliminating the nitrogen. When we do that, the nitrogen will be eliminated with two methyl groups and an ethyl group. So for that reason, we get the following two compounds: dimethyl ethylamine as the amine product that's eliminated, as well as the following cyclohexene. The cyclohexene results when we remove this hydrogen and form a double bond there. Since the Hofmann elimination typically goes after the least hinder hydrogen, we should expect that it will be this hydrogen rather than this one that is removed the most. So the products on the top most likely would be the major products. In this question, pretty similar to the last one, we have an unsymmetrical amine and we're going to do a Hofmann elimination, and we want to predict the major products from the reaction. Addition of excess methyl iodide to the amine in this question would lead to the following intermediate that has an ethyl group this way, cyclohexyl group to the left. We'll have a nitrogen going up with an ethyl group on it, as well as two methyl groups plus a positive charge on the nitrogen. We'll have an iodide counter ion. And then once we add base, we can do the Hofmann elimination. Now there are three possibilities here. We can remove a hydrogen from, so if we look at the nitrogen and count two carbons away, so this is the carbon that the nitrogen is attached from this side. On this carbon, we can potentially remove this hydrogen. If we go towards the cyclohexyl group, if this carbon has the nitrogen, we go to the next carbon, and we can remove a hydrogen from that carbon. Or if we go upward, here's the nitrogen. It's attached to this carbon, so we could potentially remove a hydrogen from the end here. From those three possibilities, the least hinder hydrogen would be the one here on the methyl group at the end. A simpler way to look at it here is a methyl group. Those hydrogens are more accessible than the secondary hydrogens here, and more accessible than the tertiary hydrogen here. As a result, if base removes the most accessible hydrogen, which is this one, and we form a double bond here by eliminating the nitrogen, we end up with ethylene as our alkene, plus the following amine, which has two methyl groups, plus a carbon that has an ethyl group to the right and a cyclohexyl group to the left. The Sandmeyer reaction is a very useful reaction that allows us to convert the amino group in an aniline into a number of other substituents around that are attached to a benzene ring. The Sandmeyer reaction involves reacting an aniline or a primary aroamine with nitrous acid, which is HNO2, to form a diazonium salt. This diazonium salt is very reactive. It's an electrophile that can react with a number of nucleophiles that leads to a substitution reaction of the diazonium salt with the dead nucleophile. As a result of this reaction, the diazonium salt is released as a nitrogen gas molecule. The diazonium salt in the Sandmeyer reaction, again, is formed by reacting nitrous acid, usually in combination with sulfuric acid, to form or convert the amino group in an aniline to a diazonium salt, which can then react with several copper salts, such as copper bromide, to replace the diazonium salt with the bromine. Another example shown here will lead to conversion of this amino group into a diazonium salt, which then reacts with copper cyanide to add a cyano group where the amine used to be. Copper chloride would do a similar reaction as copper bromide, giving you access to aryl chlorides. Without going too much into the details, it is believed that this reaction occurs through a radical mechanism where the copper adds an electron, leading to breaking the carbon to nitrogen bond, giving us this aryl radical, which then reacts with whatever X group is on the copper. It could be a halogen or a cyano group to give us the final product. Another version of the Sandmeyer reaction involves using hypophosphorus acid, which is H3PO2, to replace the diazonium salt with a hydrogen. For example, this substituted aniline, when reacting with nitrous acid as well as sulfuric acid, will convert the aniline into a diazonium salt, which then, when mixed with hypophosphorus acid, will lead to replacement of the diazonium salt with a hydrogen. Overall, we're completely removing the amino group that was in the starting aniline. Here's a second example, a diazonium salt, which would be formed from an aniline. When mixed with hypophosphorus acid, will lead to the reduction of N2 and giving us a benzene molecule in this example. Diisonium salts can be converted into phenols by heating water with the diisonium salt, as shown by this example. Alternatively, if we use copper oxide or cuprous oxide mixed in with copper nitrate, we can do the same reaction at a lower temperature. The example shown below here, using a para-methyl-aniline as an example, when mixed with nitrous acid and sulfuric acid, will give us the diisonium salt, and then mixing the diisonium salt with water and a mixture of cuprous oxide as well as copper nitrate will turn the diisonium salt into a phenol. The Sandmeyer reaction now gives us another method to add substituents onto a benzene ring. So in combination with electrophilic aromatic substitution reactions and nucleophilic aromatic substitution reactions, we can do a number of manipulations around a benzene ring. Here's a question where we want to prepare meta-hydroxyacetophenone. Of course, this would be a difficult molecule to make based on electrophilic aromatic substitution. We want to use the diisonium salt replacement reaction, or aka the Sandmeyer reaction, to add the phenol group onto this molecule. If we start the synthesis from benzene, we could do an Friedel-Crafts acylation reaction to add the acetyl group in acetophenone. And then if we do a nitration, that would lead to adding a nitro group at the meta position, since the ketone is a meta-directing group. Reduction of the nitro group with tin chloride and acid, which again can be done under other methods such as hydrogenation or lithium aluminum hydride. Either way, we're going to reduce the nitro group into an amino group. Adding nitrous acid and sulfuric acid will turn that amino group into a diisonium salt. Heating it with water, or using water and a mixture of cuprous oxide and copper nitrate, will convert that diisonium salt into a phenol.